General Physics, UT Quest problem set, conservation of momentum. This particular problem is collision of two hockey pucks. All right, this is case number 1. Two objects hit each other and bounce away from each other. The trick to this is they bounce away in 2 dimensions, but the way we solve it is the same. We just need to account for all of our momentum in both dimensions. All right, so let's start with our initial momentum. And our initial momentum can be completely defined, magnitude and direction, with these pieces of data. The mass of both pucks, the speed of both pucks, the direction of both pucks. So with all that information, I can completely define initial momentum. It's the mass of puck 1, velocity of puck 1 initially, and all the momentum is in the horizontal direction. Okay, and then we have our collision. All right, so after our collision, let's look at the data that we're given after the collision. After the collision, we're given everything that we need to know to define the momentum of the first puck. I'm given his velocity, I'm given his direction, and I know his mass. So the final momentum of puck 1, I know everything about it. Right now it's puck 2 that we need to find his momentum. Then after we find his momentum, we can find his velocity. So how am I going to go about this? Well, the key is I know everything about puck 1, so what's left over has to belong to puck 2. Let me show you what I mean. All right, if I look at puck 1, it's got a y component that I can easily calculate. That y component has to be equal and opposite in magnitude to the y component of the second puck. How do I know this? Because the y components must cancel out. If I look at my initial momentum, there is no momentum in the y direction. So that means after the collision, my momentum has to add up to 0. I can have momentum in the y direction, but it has to equal to the sum of the momentum in the y direction before the collision. That's why they have to cancel out. So if I know one, I know the other one. Okay, so I can kind of use the same logic and a little bit of process of deduction to find the x component of momentum of the second puck. All right, so this quantity I can calculate, the x component of the first puck. I have everything I need to know to get that vector. What I don't know is the momentum of the second puck in the x direction. But by default, or by deduction, I can figure it out. Okay, so here is my conservation of momentum equation. All my initial momentum has to equal to the summation of all my final momentums. Okay, all of these quantities we know except for this guy right here, this little piece of momentum of the second puck in the x direction. So I can calculate him. All right, now we know all the pieces of the puzzle of momentum for the second puck. We just need to put those pieces together. All right, well, here's our pieces. I know the final momentum of the second puck in the y direction. We just got through calculating the final momentum of the second puck in the x direction. I can get the total momentum of the second puck after the collision using Pythagorean. That will give me my total momentum of the second puck. If I needed to find direction at this point, I could. But the problem doesn't ask for it. So all I have to do is I just need to take my total momentum, divide it by the mass of the second puck, and then, let me say that a little bit more carefully. Take the total momentum of the second puck after the collision, divide it by the mass of the second puck, and I have the final velocity of the second puck. It's actually the overlying concept is pretty simple. You do need to be careful with your numbers. The calculation part can get a little tedious. There's a lot of pieces, and you need to keep track of all the pieces to be successful in this problem.